Okay, thank you, Murat, and thank you for organizing this nice workshop now for the third time. Actually, I remember back in, I think it was 2012, we had some kind of a pre-workshop in Heidelberg in my own place, and that was seen as some people called it a Woodstock for neuromorphic computing, and I'm glad to see that this is now happening each year in February, and I'm always looking forward to be here. So it's a great meeting, but of course it's very much dominated naturally by the work that's being done on this side of the Atlantic. So it has always been my role in a way to inform you a little bit about what's going on in Europe, and you know that there are quite a few activities in Europe, and you also certainly know that they are heavily criticized at the moment. I mean, these are very, very difficult times for us, and I would like to take this opportunity to tell you a little bit what we plan in the Human Brain Project, but also maybe review a little bit the history. I mean, the neuromorphic computing, brain-inspired computing, understanding computational principles of the brain in Europe, the concept was always to integrate that with computational neuroscience or also with experimental neuroscience. I mean, I was very impressed to hear that in the US now, I just learned this today, there will be a national strategic initiative for the computing, and this is seen as a partner project to the Brain Initiative. I mean, that's great, of course. It means it's a very broad kind of funding. In Europe, the strategy has always been to do both aspects, computing and biology, in the same projects, which is now a reason for critics, unfortunately. So what happened, basically since 2005, there have been a couple of projects. Funding has not been enormous, like 25 million euros or so, but of course there has always been investments from the institutes that have contributed. And all those projects, starting with facets, BrainyNets, BrainScales, and now the Human Brain Project, they always had this idea, as I said, of linking biology, theory, modeling, simulation, and then finally coming up with new computing architectures. In addition, there are still going two large national projects in Switzerland, the Blue Brain Project, and the Spinnaker project in the UK. Now, in my talk today, my little presentation here, I will mostly concentrate on the aspects on how the program is organized, but there will be two talks tomorrow by Steve Ferber, who is here, and myself on the work we actually do, the scientific work, but this will be more on politics in a way. Now, a good example on I think the European concept is this BrainScales project, which is still going until the middle of this year, basically, where people said, well, there are these different scales in the brain, different spatial scales, so there are neurons and even subneuronal elements, but of course cortical areas and even larger structures, and all those we have to understand and their interaction. But there is also time. Time is important, and we just learned that learning is an important thing, and we have to understand learning on a time scale that we can handle it. We cannot do that on supercomputers, because if you run a simulation that's 1,000 times slower than biology, you have to wait 1,000 years for the result if you want to simulate a year. And so that's just not accessible. So we have to develop the tools to understand self-organization and learning. That's one of the important things that we worked on. It's based on in vivo experimentation. It was said that experimental data have increased, quality has increased enormously, and that gives us an enormous amount of input. Computational analysis is important, but also generic theoretical principles, like, for example, ideas of how to do stochastic computing, how to implement Bayesian inference, not only computationally, but maybe also going down to the individual neuron level. Then, of course, the idea is to synthesize cortical skills, both by numerical simulations, which are very nice and flexible, but also by special computing architecture. The Human Brain Project has been conceived in 2009. Many people forget that. I mean, really, the original ideas go back to 2009, even 2008. There was a long period of preparation, and only in 2013, in October, the project started with a very small initial financial contribution of 54 million euros. It's a 36-month ramp-up period. We are in the middle of that at the moment, and now we are working hard to get something which is a framework partnership agreement. Europe has obviously these funny words. It's called FPA. You don't have to remember that. But the important thing is it's a 7.5-year planning, a roadmap. And this is really spectacular, because so far we were always going from 1, 2 to 3 year project to the next, and there was never any continuity. And now for the first time we have a chance at least to realize that if we can convince everybody working in the field. Now, the project is organized that indeed data is the basis, but it's not so much collecting data, it's also collecting data ourselves, it's also organizing data and making the data available, because there is a lot of data in neuroscience, but we don't really know how to use it. Then there are what we call platforms. These are all computing platforms. They are all related to computational analysis and computational synthesis, and then there are applications. The 6 technology platforms in HPP at the Human Brain Project are to gather information from neuroscience, from medicine, to provide the necessary tools for simulation on conventional computing machines, to provide those computing machines, because current systems with their memory and computing capability are not really able to do these simulations. Then there is neuromorphic computing, I say a bit more on that, and of course robotics. We have to expose the systems to data, and those are often robotics data. There are 2 directions. One is computing for neuroscience, and the other one is neuroscience for computing. And I think it's important that we do both. If you want to do computing for neuroscience, then neuromorphic systems are reliable, fast, efficient, and compact simulators. You build better simulation tools. If you want to use neuroscience for computing, then neuromorphic systems just provide the highest possible degree of biological complexity under user control. That's very important. So the current work is organized such that it's a typical European project going from Sweden to Turkey, basically. So there are 9 groups in the neuromorphic computing platform and 6 groups in what's called neuromorphic computing applications. Hardware-wise, the idea is, and here I have to disagree a little bit with Jacob, who said that all the progress comes from better tools to observe the brain. I think one of the problems that neuromorphic computing had in the past is that it was only used by the PhD students that actually built the chips, and it was not accessible for everybody. To me, the main goal is to change this. So we want to produce usable, useful, and configurable. You can almost call this programmable systems, and they should really be useful for non-hardware experts. I will show you some examples tomorrow. And we just don't want to do lab samples. And so after some discussion, we decided that we would go 2 ways. One is the many-core digital processor system. The other one is mixed-signal physical models. And there will be more tomorrow on that. These are the systems that are currently under construction, not the old buildings there. This is just Manchester and Heidelberg. But the 2 machines at the bottom is a many-core machine of 500,000 ARM cores, and the physical model system was 1 billion plastic synapses and 4 million neurons. And again, applications will be shown tomorrow. Now, very shortly before I close here, is that there is a roadmap now. So that's very, very important. This document there is the Framework Partnership Agreement draft. It has been evaluated by the Commission and the reviewers and received very, very positive reviews. That's maybe not known to everybody. In fact, this thing was more positively reviewed than the original project. So it's, that was a good thing, but we are now working with the people that criticize the project very strongly. There is a mediation process going on, because some people say they're not all necessary aspects, in particular cognitive neuroscience, are properly represented, and we are working on that to improve that. But this is the current document. If you're interested, it's available on the website. This is the plan for neuromorphic computing, very detailed, so I will not go into big details here, but you see, I mean, there is a part above the blue line and below the blue line, and above the blue line is building these configurable systems that are accessible to users. You see, there are a lot of tools, software tools, to configure, analyze, and use the system. There is a theoretical principles work package, so do we really work very closely with people like Wolfgang Maass, for example, to implement, for example, stochastic computing, and then there is the idea of implementing the platform. At the bottom, there are things which we want to bring in addition. It's called partnering projects. That's, of course, the applications. That is, we want to go from the large systems to small portable hardware systems that we sort of extract from the big system, then we make special chips or special little portable systems that have special applications. We want to work on devices, of course, and finally hybrid, high performance, this should be HPC, high performance computing neuromorphic systems. There is a roadmap in detail for both the physical model system and the many-core system. This also will be discussed tomorrow, but what I'm saying is that there is a rather detailed roadmap, because what we learned is from the previous projects, you know that you see that in IBM True North, you see that in Spinnaker, you see that in Brainscales, the chips that we use today, that we use to do our experiments, and I think we do very nice experiments today, they have been designed 10 years ago. I mean, 2005, we started to think, or we designed the chips that are available and for use today. So if we want to have a system in 2023, we better know exactly what we want to do. So this is our roadmap. It's quite some detail. It tells us how we integrate neurobiology knowledge. It tells us how we spin off little systems, distribute them to schools and universities and many other things. Okay, so that's the plan. More tomorrow.